Hello and welcome to a video which goes through the solution of a pipeline system analysis. Figure 3 is an aerial image of the pipeline system. So here is figure 3. See if I can center it, all nice and pretty. With preliminary engineering sketches of the system in the lower left panel and a detailed sketch of the terminal small storage tank in the upper right panel. Lower left, upper right. The 3,200 meter long pipeline carries 25 degree Celsius water from the reservoir with a pool elevation of 975 meters and supplied density and viscosity shown there to the treatment plant down here through a pump all the way up to the large diameter storage tank with a base elevation of 1,000.3 meters and a pool elevation of 1,006.3 meters, so 6 meters deep. It goes through a 127 millimeter diameter high density polyethylene pipeline with a sand roughness height of 0.0015 millimeters and to this large diameter tank, and then there's a secondary line 800 meters that carries water from the tank to the small terminal storage tank at the schoolyard. This small tank has a diameter of 1 meter. It's 3 meters, the bottom of the tank is 2 meters off the ground, 3 meters to the top of the pool. The tank has a float valve, as does this one, to maintain the water depth and to stop flow once the water is deep enough. It says both storage tanks have float valves to prevent overflow and maintain the indicated pool elevation. So let's go through some of the solutions. First question asked is, what is the pool elevation? And that I don't think is very difficult. It's 975 meters at Lake Gulameta. Then it says assume the float valve at the schoolyard fails in the open position. So if we examine what the float valve might be like, there's probably a pipe coming down here. There'll be some kind of cage, and then there's a ball here that's supposed to be buoyant. As the water comes up, it's supposed to lift the ball and stop the flow, and somehow it becomes clogged so that our system has overflow. And at overflow, we will stipulate that we are at 992 meters pool elevation as the tank overflows. So our question is therefore, what's the flow rate in this condition? So in this case, we want to analyze this portion of the system. So we have the upper tank here, going to a tank there, we know that this is 1,006.3 meters. We know that this is 992 meters overflowing. That's 800 meters of pipe. And if we write the Bernoulli's equation, we would have, let's call that position 2, that position 3. We have total hit at 2 equals total hit at 3 plus the head loss. H2 minus H3 equals the head loss, which is equal to 8FL Q squared over pi squared G d to the fifth. We know to use Darcy-Weisbach because we're given a roughness height. So as written, then we would have to come up with values for friction factor based on flow rate. However, this is clearly a case where we can apply the Jain equation. And if we do so, we want to apply the Jain equation to 1,006.3 minus 992 equals the head loss, which is equal to 8FL Q squared over pi squared G d to the fifth power. 1006.3 minus 992 equals 14.3. And to apply the Jain equation, we can go to an online toolkit. Discharge given head loss, and enter the diameter, enter the gravitational acceleration, enter the head loss, 14.3 meters, enter the pipe length, 800 of them, roughness height 0.0000015. We have to convert millimeters into meters. And kinematic viscosity is 8.94 E minus 7. Hit the submit, and we get a computed discharge of 0.02169. 0.02169, which is 21.7 liters per second. Okay, that's that problem. Using the flow rate just computed, Q equals 21.7 liters per second, 0.0217 meters cubed per second. We want to find out what the head the pump has to supply. So now we're on this part of the problem. We know that's 975 meters, that's 1,006.3 meters. This is 3,200 meters long. And so we now want to determine the added head of the pump. So we call that point 1 and point 2. We have H1 plus H sub P equals H2 plus head loss. H sub P equals H2 minus H1 plus head loss. H2 is 1006.3 minus 975 plus 8FL Q squared over pi squared G D to the 5th power. That equals 31.3 meters plus 8. We don't know the friction factor yet. We know that we have 3,200 meters of pipe. We have 0.02176 squared, divide by pi squared 9.8, diameter 0.127 to the 5th power. So let's see what we can do to get this friction factor. We do have a web-based friction factor calculator. To use it, we need to know the Reynolds number. We have a Reynolds number calculator that works in velocity, and so we're going to need to compute the velocity in meters per second. So if Q equals 0.0217 meters cubed per second, we divide that by the area, we divide that by pi 0.127 squared over 4. Doing the calculations, come up with a velocity of 1.71 meters per second. I certainly hope that's right. Escape. Okay, so my diameter is 0.127. My viscosity, my velocity is 1.71. My density was given in the problem statement as kilograms per cubic meter. .997 And my viscosity needs to be in kilogram meters seconds, so I'm going to have to go look up that. Back to my Reynolds number. Got that. 997. Velocity 1.71. Diameter 0.127. Submit. My Reynolds number is 243,000. Copy that. We now want to go to our friction factor. Supply the Reynolds number. Roughness height 0.000015. Diameter 0.127. Friction factor is 0.015, so we're going to write that down. .015, and now we can complete our calculations. And doing so, we come up with 88.19 meters. Let's call it 88.2 meters. So that's the added head that we have to supply to the system for it to work. Next part is our tank is fine, but somebody left the valve open. So a worst case approximation would be a frictionless loss or flow out of the tank. We know it's going to flow out there with a velocity. The float valve is going to attempt to maintain this level. We know that that's 1 meter tall, 1 meter diameter. We could do an ordinary Bernoulli analysis. 0.075 meters. Call that 0.1 and that 0.2. So P1 over gamma plus V1 squared over 2G plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. We'll declare Z2 the datum. Zero pressure at the top. There's zero pressure in the jet. Because this is maintaining a water surface, that's essentially zero. So we have Z1 equals V2 squared over 2G. V squared equals 2G Z1. V equals square root of 2G Z1. Multiply both sides by the area. That gives us the flow rate. And so we have pi 0.07 pi times 0.075 squared over 4. Square root of 2 times 9.8 times 1 equals 0.0195 meters cubed per second, which is 19.5 liters per second. Get on to the last part. Net positive suction head information's up here. We want to deal with the schoolyard overflow conditions, and we want to size the pump or size a pump system that can supply essentially the 21 liters per second at the required head value. So there's my 21 liters per second. And if you recall, we need 88 meters of head. None of these pump curves can supply that as a single pump. But if we run the pumps in series, then the heads will add. So it's as if we've taken that pump curve and then we double it, and we're going to operate on this squared line here, on this dashed line here. So two of these pumps in series, the effect it has on this drawing right here is simply to double these numbers. 20, 40, 60, 80, 100, 120, 140. Here's our operating point. We're after 88. So I look right about here, and I'm almost, that's a head of about 90 meters at 21 liters per second. Shut off is, I'd say that's about 96 meters of head, and at 30 liters a second, well, let's go to 35, I think that's on the curve, I'm at about 67, about 75. Whoop, I don't want to be up there, I want to be down here. My bad. $70 meters ahead. So my pump curve for 2 pumps in series is going to be that, and it's going to have these 3 points. Now the reason I'm doing that is I have an online tool that allows me to enter a 3-point pump curve, other parameters of the system to see how well it's going to function. So let's use that tool. Pump flow between reservoirs, 975, 1006.3, 3200, 0.127, 0.000015, 8.94 E minus 7, 9.8. At shutoff we have 96 meters. We have 90 meters at 0.02176, my guess. And we have 70 meters ahead at 0.035. So that's taken off this curve. And it claims we get a Q of 0.021 meters cubed per second, which is 21 liters per second, and that's at 88.009 meters ahead. So that would be pretty close to what our target is. The net positive suction head is around 2 meters. And then the last part is the estimation of the net positive suction head available. For net positive suction head available, we have to have the head of the vapor pressure, we have to have head absolute. We'll do head absolute first. Air pressure at 1,000 meters altitude. Hopefully the air pressure calculator will work. Give us the altitude. Calculate air pressure at altitude. Supply at altitude, so I'm going to put 1,000 meters. Our lake's at 975, that's close enough. It says that our air pressure is 89874.54 newtons per meter squared. We're going to divide that by the value of specific weight of water at 25 degrees Celsius, which is 9781 newtons per meter cubed. That we got from an online tool. We'll go look at that real quick. That number right there. And while we're here, we have the vapor pressure of 3170 newtons per meter squared. We're going to divide that by 9781 newtons per meter cubed. perform the indicated arithmetic. $3,170 divided by 9,781, 0.324 meters of vapor pressure, 89874.5 divided by 9,781, 9.18 meters of absolute head. And now we have an online tool to help us with the net positive suction head available. So we go to that. Even though it says it's in US units, as long as these are entered in length units, so feet or meters, it will produce a correct result. It's going to label it with the wrong unit, but it will still be the correct result. So the absolute is 9.18. Our static head, in our case, our pump is 10 meters. Let's see, 965, 975, 10 meters below the base, below the pool elevation, at least from the drawing. So we have 10 meters of static elevation, and you use the minus value if the water is above the pump. Minus 10, said neglect friction, 324. And it claims that our NPSH available is 18.8 meters. So we'll go ahead and write that right here, and we are complete. 2 of these pumps in series will satisfy this hydraulic system. If the valve is left open, we're already producing over 21 liters per second, so it can handle the valve left open. It can handle the overflow case. We have a pumping system that produces the required 88 meters a head, and we also have enough to accommodate the overflow condition. So this would be an effective preliminary design for this system. That concludes the recording. I hope you enjoyed it.